The following shows the electric field and the electric potential for a dipole in the color gray as well as blue. And so the values could be seen with the vector, in which the length corresponds to the magnitude of the electric field and the direction is the direction of the electric field, and the number phi in there corresponds to the electric potential. And all of this is computed by only using Coulomb's law. So in this video, I will be discussing about electrostatics, starting from Coulomb's law, and then we'll be going into the idea as to what is a dipole and a quadrupole and etc. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout the entire discussion. So let's first talk about the electric charge. So the electric charges or the observed throughout our life, as if you try to rub certain objects together, you get charged objects. And so observing these charged objects, people start to try to figure out what exactly is a charge. And they found the source of the charge, which basically comes from the electron and the proton. And these are something which we call as the elementary charge, because you cannot get anything smaller than the elementary charge. Even though there's the up quark, down quark, they have the fractional elementary charge, but they cannot constitute on their own. So this is why our elementary charge only consists of the magnitude of the charge of an electron. And these electric charges are scalars, and they go from negative values to positive values. And so that will later be discussed later on when we'll later talk about the Coulomb's law as how different charges attract each other. But we see that charged objects and these elementary charges are the one that is constituting to certain behaviors throughout our physical world. And so if we observe this in the big scale, we don't care about each of the charges as how many protons and how many neutrons, no, how many protons or how many electrons, but what is the net charge instead. So you could just sum up of the negative charge and of the positive charge, and it will pretty much constitute to the charge of the entire object. And also there's something important about charges is that the net charge is conserved in a closed system. So this basically means that you cannot increase or decrease the net charge. The net charge has to be the same for a closed system. So let's talk about the Coulomb's law. So the Coulomb's law is a law that is written thanks to the observation of the physical world. And so this is something that Coulomb figured out. First is that for the charge, there's only two types of charge. Two types of charge, which is positive or negative. And secondly, it is also observed that the force between these two charged objects is proportional to the r squared if the charge doesn't change. And it is also true that if you have like charges, Q1 and Q2 is positive, it will try to repel each other. And so this is denoted as the r hat. While something that has differing charges, differing signs, will later attract each other, which is already given from this formula in itself. So what we can observe now is that we can just write down what is the force, which is the proportional constant, multiply that by, oh sorry, this is 1 over r squared technically. So it's the proportional constant multiplied by each of the charges in the r hat direction over the distance r squared. So instead of writing it like this, we can just denote r12 to be the vector from r1 to r2. Basically, it tells you the position from point 2 to point 1. So this is the force at 1. The force at 1 would be a proportionality constant times q1, q2 in the r12 direction, right? So this is r12 squared divide that again by R12, which will later give you the unit vector. And so this is basically the Coulomb's law. And so with only experiments, you could figure out what is the Cu here, which is 8.9874 times 10 to the power 9 Newton meter squared per Coulomb squared for SI units. And this is basically the definition of the Coulomb in itself. You could also define it to be a value of 1, but instead we use the unit Coulomb because it is already known that within electricity you are using the terms amperes. And so to make sure that the definition of amperes is conserved, you use the idea of coulombs. But normally people don't use this value when it comes to physics. Instead, Cu is defined to be 1 over 4 pi epsilon 0. And this will later be explained once we get to Gauss Law. So epsilon 0 in here could be defined to be 1 for certain units, but in here, for SI units, it's 8.854 times 10 to the power negative 12 Coulomb squared per Newton meter squared. So something interesting about the electric force is that you could just sum up each of the components and you would get the force for the entire system thanks to all the different pairs of forces. So we could rewrite our Coulomb's law into a much more general form. Fi is just Qi over 4 pi epsilon 0. That's basically the entire constants, right? Sum them up for all of the j's and I, when j is not I anyways, until a certain value n, which will be so the qi is already out, so it's qj over rij cubed in the rij direction. So something that I want to show here is that you could just sum them all up because of each of these small charges. But if you actually refer to 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 how small the elementary charge is, it's 1.6019 times 10 to the power negative 19 coulombs, which is a very small number to what we normally observe throughout our daily life. And so therefore, we will just ignore the idea of the discreteness of such elementary charges and instead think about a continuous charge distribution. So this will later have the idea of the volume charge density and the surface charge density. Volume slash surface charge density. So this is just given based on the normal formula for density. So for volume, it's rho equals to the Q over V. For the small q's over a unit area, the limit as the delta V goes to 0. And for the surface, it's the same. It's the charge over the surface instead. Limit as the delta S goes to 0. So you could now get what is the small q's, and then if you try to flip them all around, you could get the electric force to be a much more elegant formula that works for discrete particles, for the continuous charge distribution, for the volume and the surface. So it is written as Q, so we'll just be assuming that we'll be at point Q anyways. So the force at Q will be Q over 4 pi epsilon 0. And this will be for the discrete charges, which will be the Qi prime r vector minus ri prime over r minus r prime I cubed with r minus r prime I direction. Sorry, so it's like the magnitude of r vector minus r prime I. So the prime here denotes the position of the charges corresponding to a certain reference frame. So that's for each of the discrete objects. And then we'll be considering the surface, which will be the integral instead of the summation, because summations and integrals are the same thing. So if you substitute the definition, it would be r vector minus r vector prime over r vector minus r vector prime, the length cubed. Oh, sorry, this shouldn't be there anymore because this is already written. So we got this one and the surface charge density in terms of the r vector primes, and you do the surface integral or the dA prime for the surface. And you could do the same thing for the volume. So it's the same thing as before, r vector minus r vector prime cubed with the volume charge density dV prime. And this is basically the Coulomb's law for any type of system that you have. Now let's use the discussion of the electric field. And why do we use the idea of the electric field? And so this is something that I want to show you, is that what we see here is the force at point Q will depend on a certain number as well as this Q in which you could change. So what you could do instead is define an electric field, which is the limit as the Q goes to 0, or basically for a very small charge. And the definition is just the FQ over Q. So now if we observe something like this, we could just denote what is the electric field based on the Coulomb's law that we got, which is 1 over 4 pi epsilon 0 with the sum as I 1 until n of the Qi's prime of r vector minus r vector prime I over the length of r vector minus r vector prime cubed plus the integral r vector prime over the magnitude cubed with the surface charge density and also with the volume charge density. So based on this, we know that this unit is newtons per coulomb. So what we observe from here is that basically if you have an electric field, which is given by this formula, you could know the force for a certain charged particle by only multiplying this electric field with the charge, and this will straightaway give you the force. So this could be seen as like lines of force, basically. Lines of force that doesn't really depend on the charge. This is pretty similar to how we defined the gravitational field back when we did General Physics 1. So if we refer back to the idea of the dipole that I have shown in the simulation, we have this electric field here to be shown as this gray lines. And these gray lines here actually doesn't tell you about the direction. There should be an arrow pointing, but I didn't put that in. And so instead I put a test charge in which it tries to circle around this dipole, and it shows where is the electric field pointing as well as the magnitude. And so that's basically also the force if the charge is positive. And so that's the definition of the force for a point charge. It's just Q times the electric field. So let's jump to the idea of the electrostatic potential. So let's just take the component from the volume charge for the electric field. So it will be just this component with the volume charge density, r vector prime cubed, rho r prime dv prime. Okay. So you could just do the same thing for the other components, but in here I'll just only focus on this particular integral. And so we will just try to consider what is the curl of such electric field. And if we try to observe this closely, because the curl here is just something that is corresponding to the XYZ, not the positions. So what we know is that it will only influence the fraction part at the front, which is this part. R vector minus R vector prime cubed of the rho R vector prime dv prime. So it's just only influencing this front part. Now you could try to evaluate what is the component at this front part here. And let's just actually try to solve this. So we know that there is a fact if you are doing computations for a scalar multiplied by a vector field for the curl, it's the curl of the vector field multiplied this by the scalar, and also you just need to find the gradient of the scalar, and then you cross it with the uh, vector field. So this is discussed at the last video. But anyways, if you try to compute this for this particular problem, the front part will be the sorry, so let's just reverse the order. So it's the scalar first. So it's the gradient of 1 over r vector minus r vector prime cubed multiplied cross the r vector minus r vector prime, and then you add it with the scalar at the front, multiply that with the curl of the r vector minus r vector prime. And so something that to note here is that r vector minus r vector prime, it's if you remember for the curl, uh you could just denote this into the curl of the r, in which r is just r vector minus r vector prime, right? And so observing this as just the curl with respect to this r, with the reference frame in r of the position vector of r, and that's definitely 0. So we know that the backside here is definitely 0. What about the front part? So trying to evaluate the front part here, so this is just a function based on this r vector as well, right? So we could just denote this as the same thing, right? So it's just 1 over r vector length cubed, or basically we could just denote this as only the r. So it's 1 over r cubed. We are trying to figure out what is the gradient of this 1 over r cubed cross later the r vector. So just doing this and remembering the formula, this would be just the r vector over r, and the front part would be just the integral. Sorry, the derivative with respect to r. It's negative 3 over r to the power 4. Yes. And then you cross this with the r vector. Now, you don't need to have advanced calculations from here, because you just only need to notice that r vector cross r vector is 0. So this entire thing is 0. So what we observe is that the curl of the electrostatic field is 0. And so if you remember from a property from the vector calculus, we know that the curl of a gradient is always 0. So, sorry, so instead of phi, let's just denote this as psi. And so with this, we will just denote E vector to be negative gradient of phi, where phi is a scalar field. And so the negative is only from convention, but you will later see why we actually put this negative sign at the front. So we can try to solve what is the phi because of the properties of the integrals. So if we take from a reference frame until r of the E vector, the r vector, it's the same thing as the changes in the phi. So it will be the negative, we'll just bring the negative there. This is the phi r, this is the reference, which will later be 0, as that is what we'll define that to be. So we can later just try to substitute this in. I think we'll just substitute this now. And we'll just only denote the one with the volume charge again, because it's the most simplest thing to actually write down. And it is in general form anyways. Like so. with the dr vector as well. And this would equal to d phi r. And so something that I could show here is that dv prime and dr vector doesn't depend on each other. So you could just switch the order and do the integral. And so doing the integral of this guy, it would be just the integral for the volume of the charge density in the r vector prime, right? Divide that by the length of r vector minus r vector prime, dv prime. And that's basically the electrostatic potential. No, sorry, there should be a 1 over 4 pi epsilon 0 here. So there should be a 1 over 4 pi epsilon 0 at the outside. So we get that the electrostatic potential is, in general, it's going to be 1 over 4 pi epsilon 0 of the sum of I equals to 1 until n of each of the point charges, r vector minus ri vector, plus the one from the surface, which will be sigma r vector prime over r vector minus r vector prime, the length anyways, of the a prime, and the volume, r vector prime over r vector minus r vector prime, dv prime. So if you refer back to the simulation that I've shown earlier, what you see is that you could see that the blue lines, or the equipotentials, are always perpendicular to the streamlines, or basically the electric field. And this is something that you have already seen in the first video, in which I discussed about the relationship between the function and the gradient, in which it is always perpendicular if you observe it in terms of the equipotentials. Something else to note is now, thanks to this, we get the relation that the E vector is just the negative gradient of the scalar electrostatic potential. But if we multiply both sides by Q, we get something that is very interesting. This is just the force, which is the negative gradient of Q phi. And this is negative gradient of U, thanks to the definition of what is the force and the potential energy. So the potential energy is just Q multiply that by the electrostatic potential. This is why we put the negative at the front, is to get this type of relation. And so from this, we can observe that the unit is just joules per coulomb, or we normally denote this as the voltage instead. So let's talk about the differences between two different materials that when it experiences this electric field, it behaves in two different ways, which are the conductors and the insulators. So conductors, they let charges flow, and this is because of their free charge carriers. So basically, conductors have these free electrons such that it can move in any single direction thanks to the application of the electric field, which gives them force anyways. And in insulators, instead they are bounded. The charge carriers are bounded. And so because of this boundedness, they cannot move their electrons around unless if you apply enough energy. Or basically the electric field is applied. And so this is something which you call as a dielectric instead. So insulators are basically dielectrics. And there's also another type of material which we can discuss, which are semiconductors. So semiconductors behave more like conductors when you are applying it with a electric field. It has those free charge carriers. But when it comes to a changing electric field, it behaves more as an insulator. And so this is why it is called as a semiconductor, because its property isn't really a conductor, but it's also not a insulator as well. And if we discuss about a conductor, because the electrons are free to move, the electric field, the total electric field in a conductor have to be zero. And this is why. If there is electric field inside the conductor itself, what that means is that charges are still able to move. And this is not really this is not really electrostatic. Instead, the electrons are still moving. And so therefore, you need to have the force to be zero, otherwise you'll be inducing movement inside the material. And so within static, inside a conductor, the electric field has to be zero, even though that inside there could still be some more charge carriers. So now let's start the discussion of Gauss law. And so this is a much more powerful tool that is used instead of the Coulomb's law, but they're both the same thing. And let me show you how do you get from the Coulomb's law into the Gauss law, starting with the point charge version of the Coulomb's law, which is the following formula. But instead of doing it like this, we'll just denote this to be just the r vector over r cubed, because we're denoting the position to be zero, just to make it simple. And so what we do is that we want to figure out what's the surface integral of such point charge of the electric field. So we got this, right, or dot n hat dA, which is the same thing as q over 4 pi epsilon 0, which are constants basically, and the integral of r vector dot n hat over r cubed dA. And so this is for an arbitrary surface. It might it might change for different surfaces, but let's just denote that this is an arbitrary surface that encloses the charge first. So now if we have this point charge and then we have this arbitrary surface here, we could just grab a line, something like this, and this is our surface, right? Or basically the small surface. We got the n hat in this direction, and then we got our r vector in this direction, okay? Or the r hat. And so dotting these two values will be projecting your surface into this part here. And this distance here is r, right? And so now observing that this is basically just the projection into this plane here, if we try to scale it down to a very small scale in which the radius is just 1, we could just construct a circle that is composed of each of these ds's. So we got each of the ds's here, and also the area would later be reduced by 1 over r squared. So this would be 1 over r squared of the ds prime. So this is ds prime. So now if we now think of this much more closely, ds prime is the ds times the r vector over r dot n hat. And then if you divide that again by the 1 over r squared, or basically the one that is scaling your area down for the surface integral, this would just give you 4 pi, because this is the solid angle. So you would get the q over epsilon 0 here. And this is Gauss's law. And you could make this into a much more general form for the q to be a charge distribution. So instead, you could just write this down as E vector dot n hat dA is just the q enclosed over epsilon 0. And so this is the thing. We don't care what is the distribution. We don't care about how many different charges are there for a certain point. What we care about is that if you just draw a surface inside this three-dimensional shape, and figure out that the net charge inside is q, you could just use this formula to get what is the flux, or basically the electric field that is coming out of this surface. So this formula in itself doesn't really solve for the entire electric field for each of the points. So we could do something much more better, and that is just to use the principles from vector calculus, since this thing could be rewritten as the integral of v of the divergence of E vector, dv. This was to equal to the integral of the rho, uh, rho dv, right, over epsilon 0. So what we observe here could be turned into this divergence equals to rho over epsilon 0. And this is the differential form of the Gauss law, which is a much more useful tool if you don't know about the symmetry or such other things, but you know about the charge distribution. So let's talk about some certain applications of the Gauss law. So let's just observe a uniform wire, no, sorry, a uniform rod with linear density, let's call that lambda. So basically lambda is just a Q over L, technically something like that. And the question is, what's the electric field at distance r? At distance r, what's the electric field? So this is something that you need to note first when using a Gauss law. You should know about the symmetry. Well, we know that it is going towards infinity, so the components in the horizontal directions, sorry, in the directions of the rod doesn't really matter. And so maybe we could just construct a surface, something like this, and maybe we could figure out what is the electric field in here thanks to the symmetry. So if you do this with length, let's say this is L, and doing the surface integral, the component in this surface would be 0, and this surface would be 0, and therefore it will be just the integral of the EdA of the blanket, basically, and this was to equal to the rho, and this was to equal to the Q over epsilon 0 of the enclosed. So it's lambda L over epsilon 0. And the blanket in itself has symmetry. So the electric field at every single point here must be the same. So the E doesn't really change, and therefore it's like a constant. So we could get the E times the A, which is 2 pi r, so distance of r, right? Multiply this by the length. This was to equal to lambda L over epsilon 0. Thus, you would get your electric field to be lambda over 2 pi epsilon 0 r. And you could also get what is the potential just by doing the negative grade, just by trying to solve it through integrals. So sorry, this is in the r vector direction because of the symmetry as well. So just doing the integral, you would be able to get that this is lambda over 2 pi epsilon 0. Oh, sorry, this is r hat direction. So it's lambda over 2 pi epsilon 0 natural log of r plus c. This is the potential for the rod. So that's one example. Another example is for a conductor. For an arbitrary conductor, we know that the electric field inside is 0. And so we'll just consider a very small section here and figure out what is the electric field here. So if you take this very small surface, and let's just denote a very certain type of objects, and let's just denote that towards the left and the right because this thing is a very small object. This side is 0, 0, the bottom side 0, and all of the other blankets. So what you would have is only the top surface. So the E times A would be the the charge inside of this surface. Let's call this let's just call the area to be A anyways. So it's just A times the surface. So for a conductor, let's just assume that this is a constant A. And so for this conductor, let's say that it has a surface charge density, so we'll have the sigma here. It doesn't have to be constant because this is very small. So this would approach to a certain number anyways, over epsilon 0. So you would get the E to be the sigma over epsilon 0. And this is just the area, no, sorry, this is the electric field for a conductor. So now let's talk about the electric dipole. So for the electric dipole, if you try to consider for two different charges, so if you have a negative and a positive charge here, separated by a distance of L vector, the question is what is the electric field? So you could just do it using the Coulomb's law, which will be r vector minus r vector prime minus L vector over r vector minus r vector prime minus L vector. So r vector is your position vector, and r prime is the direction towards the negative charge. So that's the thing. So you would have this component as well as for the negative component, r vector minus r vector prime over length of, this is length cubed. Length of r vector minus r vector cubed, something like that. And so something that you could do from this is that if you realize what r vector minus r vector prime minus L vector, length cubed is just the r vector minus r vector prime squared minus 2 r vector minus r vector prime dot L vector plus L squared, everything to the power of negative 3 over 2. Sorry, yeah, this is negative 3 anyways. You could just rewrite this in terms of a Taylor series technically. So it could be simplified further into the r vector minus r vector to the power negative 3. Multiply this by 1 plus 3 r vector minus r vector prime dot L vector over r vector minus r vector prime squared, and etc. We'll just ignore the L squared terms. And so you could just instead write down your electric field now into a much more simpler form, which will be Q over 4 pi epsilon 0. It's gonna be 3 times r vector minus r vector prime L vector over the length of r vector minus r vector prime to the power 5. Oh, sorry, there's a dot there, and then there's another one. R vector minus r vector prime there. Subtract this by the L vector over r vector minus r vector prime cubed. And so this is when the L goes to 0, right? So maybe we could denote a certain value, let's say P vector, which is QL vector. And so this is just a definition to simplify our entire writing. This would be 1 over 4 pi epsilon 0 of 3 r vector minus r vector prime dot P vector over length of r vector minus r vector prime to the power 5 r vector minus r vector prime minus P vector over r vector minus r vector prime to the power 3. Now, this is a very hard thing to see as to what does this entire thing mean. So P vector is something which we call as the dipole moment. And so it will later be seen more as a dipole moment once we actually talk about the multipole expansion. But let's, instead of looking at this in terms of a vector, maybe it's much more easier to view it as a scalar, or basically just the electrostatic potential. So we could just write down what's the electrostatic potential. It will be a much more simpler formula. R vector prime minus L vector minus 1 over length of r vector minus r vector prime. Now, r vector minus r vector prime to the power negative 1, minus L vector, could be re-expressed into the same idea as before, and thus we could get the expansion of r vector minus r vector prime multiply this by 1 plus LR vector minus R vector prime over over R vector minus R vector prime to the power 3 plus blah blah blah. And thus, you could actually simplify this into the electrostatic potential to be Q over 4 pi epsilon 0 of L dot R vector minus R vector prime over R vector minus R vector prime cubed plus some other values here. And using the same definition of the dipole moment, we see that the dipole moment dot R vector minus R vector prime here, divide this by 4 pi epsilon 0 R vector minus R vector prime cubed, is pretty much the approximation of the dipole moment. Sorry, the the electrostatic potential of the dipole moment, of the dipole, in terms of the dipole moment. We could also try to view what is the energy, the potential energy, when you put a dipole moment in a external electric field. So it would be, there will be a negative q phi external of the r vector, which is basically the potential for the negative q, as well as one for the positive one. And so you could just expand this into a much more beautiful form, r vector plus L dot the gradient of phi external r vector. Or basically, this is just another Taylor expansion in terms of only the one value. So this would become L vector times the gradient phi of the external in the r vector. Or basically, it's just the, sorry, there should be a q there. This would be just the dipole moment, the negative dipole, yeah, it's the negative dipole moment dot the external electric field. This is the potential energy for a dipole experiencing a external field. So this is the discussion of the dipole, but not exactly a true dipole, but instead we use an approximation to get a point dipole. And so we can actually do this for a multiple expansion. So what this basically means is that you're expanding your Coulomb's law and doing it for each of the different configurations of the properties, such as a dipole, quadrupole, octupole, and so on. And so this multiple expansion will be done for this following potential function. So it's 1 over 4 pi epsilon 0 of the integral of rho r vector prime over r vector minus r vector prime, the length, dv prime. So we can use the same approximations for the bottom side. And so the reciprocal of the magnitude of the positions would be 1 over r of 1 minus 1 over 2 negative 2 dot r 2 r vector dot r vector prime divided by r squared plus r vector prime squared over r squared, and then you add this by 3 over 8 of r, sorry, 3 over 8 of the 2r dot r vector prime over r squared minus r prime over r squared, everything squared, and so on. So now if you try to simplify this entire thing, what you could get is 1 over r plus r vector dot r vector prime over r cubed plus 1 over 2 of 3r dot r prime squared over r to the power 5 minus 1 over r of r prime over r squared, and some other terms which we will ignore for this case. So now if you put this into the potential law, sorry, for the potential of the electrostatic field, you would get 1 over 4 pi epsilon 0 of 1 over r with the integral of rho r prime dv prime for the volume plus 1 over r cubed, sorry, r vector over r cubed dot the uh, the volume charge density multiplied by the position vectors dv prime plus 1 over 2 of the integral of v of uh, let's just do the thing inside first. It will be the sum of xi and xi prime, everything here squared, divided by r to the power 5. Sorry, at the front there should be a 3. There we go. Subtract this by the sum of xi prime squared over r cubed. So this is just the same thing. Minus the Kronecker delta of ij r prime squared of rho dv prime. And this is our q. So this is the quadrupole tensor. And there is also some other terms within this expansion. So this is denoted as qij anyways. And so qij here is pretty much a matrix. It's a 3 by 3 matrix in which it has 9 variables, and it is also a symmetric matrix. So therefore there's technically only 6 independent, but also there is also another property that actually is governed by the trace of the matrix. Thus this is actually a matrix that has only have 5 independent variables. And so this approximation is pretty useful when you're trying to solve for a much more advanced problem that requires you to sum up each of the different particles if you have a continuous charge distribution. And so with this would simplify your problem into terms of 1 over r, 1 over r cubed, and 1 over r to the power 5. So the last thing that I want to discuss is the Dirac delta function. Dirac delta function. So we know about the Kronecker delta, in which I equals to j must be 1, otherwise everything else is 0. So if you extend this for the idea of a function, you could have this Kronecker delta of this r vector here to be 0 when r vector is not 0. And it also has the property that when you integrate this for all of space, the Kronecker delta, of the Dirac delta, r vector, prime, dv prime, would be 1. So basically, if you try to figure out the volume of such function, the volume would be 1, even though that at every point it is 0. And this gives you a certain property of this Dirac delta function, is that if you do the Dirac delta of any type of function, dv prime, this would be just the function in itself. So it's pretty much just giving you the value at a particular point. So now you could consider about the electrostatic potential and try to figure out what is the potential for a point charge, or basically when it is within Dirac delta. So we'll define this to be q delta of the r vector minus r0 over r minus r0. Sorry, not r0, but r prime. And we'll be doing this for the dv prime. And so if you observe this, the solution will be just q over 4 pi epsilon 0 r vector minus r0. And this is already the solution. So we could also try to figure out what's the electric field. It's going to be 1 over 4 pi epsilon 0 of the volume charge density, multiply this by r vector prime over the length of r and r vector prime cubed dv prime. And this will later give you the solution of q r vector minus r0 vector over r minus r prime cubed. So this is pretty much just the formulas for the point charge. So now you could try to figure out what's the divergence of this electric field. It's gonna be 1 over 4 pi epsilon, the q over 4 pi epsilon 0 of the divergence of r vector minus r vector 0 over the length of r vector r0 vector cubed. And from the Gauss law, you would know that this is just rho over epsilon 0. Or in this case, this is q Kronecker delta, q times the Dirac delta, r vector minus r0 vector. And so here's something that I want to remind you, that we don't even need to use Gauss law. Instead, we know that Gauss law comes from the idea from Coulomb's law. And we have already used Coulomb's law to get this. So basically, this and this must come from the mathematics. And so we could actually simplify this further. The divergence of this function here, minus r0 vector cubed, must be 4 pi of the Dirac delta. And you could observe something much more further. You could see that this thing here is just the negative gradient of 1 over the length of r vector and r0, right? So, and this is also basically coming from the definition of the E as well, which is from the top here. So negative gradient, so the negative Laplacian of 1 over the length of r vector and r0 vector is the same thing as 4 pi Dirac delta of r vector minus r0 vector. And this is a very important equation for you to remember, or an identity for you to remember. And so that's all for today's video on electrostatics. And so in here we observe that we have lots of computations regarding integrals as well as the charge distribution. But later on, we will later observe a much more simpler way to solve any type of electrostatic problem through the boundary value problem. And so that's all for today's video. Make sure to like and subscribe, and also please share this to your friends who want to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.